Hi everyone, I am Dan Wu from Peking University. In this talk, I will introduce my research on finger motion tracking with Wi-Fi signals. This is a joint work with my supervisor, Professor Daqing Zhang, at my colleges. Finger gesture is a natural way for human-computer interaction. There are many applications that can benefit from finger gesture input, such as interacting with smart devices. But tracking finger motion in the air using commodity Wi-Fi equipment is still not possible. The most recent Wi-Fi-based motion tracking systems using commodity Wi-Fi device achieve sub-meter level accuracy. They can track human motions but not centimeter level finger motions. Considering the wavelength of Wi-Fi, which is about 6 cm for the 5 GHz band, the centimeter level finger motion has to be tracked at sub-wavelength level granularity. However, CSI in commodity Wi-Fi devices contains severe noises, such as the power amplifying uncertainty in amplitude, and carrier frequency offset and sampling frequency offset in phase. The added CSI noise destroys the orthogonality of the phase and amplitude of CSI, making sub-wavelength level motion tracking impossible. Instead of denoising CSI waveform and synchronizing phase offset as did in previous work, we propose to construct a channel ratio of CSI of 2 antennas of the receiver device to cancel CSI noise. As the CSI noise is almost identical among antennas on a receiver, they can be cancelled by division, and we get a new base signal of CSI quotient. It has a much higher signal-to-noise ratio. The CSI quotient can be simplified as a form of Mobius transformation that maps the signal between the ideal CSI and CSI quotient. Consequently, the CSI quotient has similar sensing properties as CSI. For example, the CSI quotient also has a circular trace on the complex plane if an object is moving. We can see in the figure that if the reflection path length changes for one wavelength, then the CSI quotient is a circle. The circular trace is proportional to the length change of the reflection path. So in many cases, we can use CSI quotient instead of the noisy CSI for sensing purposes. CSI quotient has orthogonal amplitude and phase information. It is crucial for microscale motion sensing. Now let's see how CSI quotient helps to extract finger motions. Consider drawing a letter D with a finger. According to the freenet zone theory, given the position of the transceiver devices, the drawing involves increment or decrement of the reflection path. Based on that, the drawing can be segmented to several pieces. Each piece contains an increment or decrement of signal propagation path. Accordingly, the CSI quotient has the same number of circular arcs. The different placement of wireless transceiver device pair has different freenet zones, thus the segmentation of the same drawing may be different. The motion displacement can be extracted from the CSI quotient arcs. They are processed piece by piece and combined together. For each arc, we first estimate its phase change by measuring the slope changes for the tangent lines on the arc. It involves the subtraction of 2 consecutive sample data. Then we calculate the reflection path length change as well as the motion displacement. The extracted displacement from one Wi-Fi transceiver pair is not enough to recover drawings. We add another receiving device as the second transceiver link perpendicular to the first one to provide additional displacement information. The 2 receiving devices have different segmentation for the drawing. Despite that, the motion displacement is aligned by receiving time on the 2 devices. With the information from the 2 dimensions, we can reconstruct the finger drawing trajectory iteratively. We evaluated the tracking accuracy using some templates. The overall median tracking accuracy is 1.27 cm. After that, we use a finger to input text. The recovered drawings can be recognized at a rate of 93% using an online OCR service. To summarize this talk, we have three conclusions. First, we proposed a CSI quotient model. It cancels CSI noise and maps the CSI quotient to reflection path length change at the granularity of the sub-wavelength level. Second, we propose a method to reconstruct the motion of FingerDraws. It pushes the tracking capability from sub-meter to centimeter. And last, we evaluated the system under various conditions. We believe that the model and techniques not only works for Wi-Fi signal, but also have the potential to benefit other wireless sensing systems, such as the fourth generation LTE and LoRa signals. For more information, please refer to our paper. Thank you.